Hello students, good morning. This is Somen this side. So today we shall be continuing Gauss's theorem as we have checked in our previous classes that as we know E dot ds closed integral over E dot ds, this is surface integral, okay, is equal to q upon 4 pi q upon epsilon naught. This is your Gauss theorem. I think it is visible. Okay, it is visible. This is your Gauss theorem as from the previous class. So this is surface integral. Okay, three types of integral are given to you. One is line integral. When you are studying higher mathematics or higher physics, you shall be taking the help of line integral, surface integral, and volume integral as well. So just get into this mind that it is, as it is being integrated with a surface, it is a surface integral. Okay, you will get to know about other integrals also. So this is what, this is Gauss theorem. So why is it important? Because sometimes it's become more complex for us to calculate the electric field of a given object where charge um, distribution is uniform or not uniform. This becomes quite complex by going through the traditional method of finding electric field by using Coulomb's law or by superposition principle. So this became more complex, but by the application of Gauss law के यूज से हम काफ़ी ऑब्जेक्ट्स का और काफ़ी चार्ज डिस्ट्रीब्यूशन का हम इलेक्ट्रिक फील्ड बहुत इजीली निकाल सकते हैं. सो टुडे वी शैल बी स्टडिंग दोज applications, but before that you need to understand that in the previous classes I had to imagine a sphere. To prove Gauss's law. What is that sphere? And the sphere is a Gaussian surface. So what is a Gaussian surface? Gaussian surface, maybe it can ask you definition of Gaussian surface. So you can write it is a hypothetical closed surface which encloses the charge under consideration. Okay, so a Gaussian surface is a hypothetical closed surface which encloses the charge under consideration. So it depends upon you. To choose that Gaussian surface. You can choose it. So why do you choose it? It is used to evaluate. The surface integral. Just this thing. We are going to write this thing off here. It is used to evaluate the surface integral. Which surface integral? The surface integral of electric field. Surface integral of electric field associated with the charge and whose result what is this? This is flux, and whose result would give you the value of electric flux through that surface, through that surface. So you need to consider a surface. You need to imagine such a surface through which some flux is going through, and you need to calculate that electric flux. And for this electric flux, we need to evaluate the surface integral of electric field associated with that charge under consideration. Okay, this is what about your Gaussian surface. So first of all, if anyone asks you about Gaussian surface, what is Gaussian surface, you can say that it is a hypothetical closed surface. Okay, not an open surface, it is a hypothetical closed surface which encloses the charge under consideration. It encloses the charge under consideration. And what is its use? It is used to evaluate. You can write the exact law in this context if you want some more marks. As first of all, we knew that the how to define the direction of the area vector. How to define the direction of the area vector. As you know, for an area vector, you can calculate or define the direction as the normal to the surface at that point, at which point we are going to calculate. But sometimes it is not so. Like if it is a closed surface, like this, then what is the area vector? So that area vector is at that point is normal to it. That area vector at that point is normal to it, but it is outward normal, not inside it. It is outward normal. But it is not possible for something that is given that it is always a closed surface. That may be this surface. It may be this surface. Then how are you going to calculate or define the direction of that normal? So first of all, such surfaces are given to calculate the surface integral. Okay, calculate the surface integral. If surface integral is to be calculated, then the direction must be specified, that it is clockwise or anti-clockwise. It is clockwise or anti-clockwise. So it will depend upon you that you are going to take the system clockwise or anti-clockwise. If it is clockwise, then you shall be defining a given direction like outward normal, and if it is anti-clockwise, then you can define the direction inward normal or vice versa case, whichever case is given to you. Okay, this was only for short notes. So this is what about our Gaussian surface. So Gauss's theorem is used to calculate electric field of complex systems, okay, easily, by easy process. The approach is very simple in this theorem, but when we are going to calculate the electric field of such complex systems via the traditional methods, by principle, by superposition principle and something like that, it will take us a very long time, and we can calculate that, but it will consume a lot of time of us, and maybe this time will get wasted. But by the use of the Gauss theorem, we can actually calculate electric field in a very easy manner. Okay, so now you can see from the next topic which I will be going to teach, that you can actually derive Coulomb's law from Gauss law. You can actually derive Coulomb's law from Gauss's law. And how is that? Let us see how are we going to derive that. It is very easy. It will confuse you that Coulomb's law is the first basic law of electrostatics, or Gauss law is the basic law of electrostatics. As when we were studying, we read Coulomb's law, and now we say that we can derive Coulomb's law from Gauss law. Okay, so the question is derive Coulomb's law of electrostatics from Gauss. This is what your heading is. This is what our headings are. So, in order to derive Coulomb's law from Gauss law, we need to consider a charge. First of all, consider a charge at a point O. This is our point O. This charge is Q. So, write alongside with me. Consider, or let us, as it is said to derive, you are not deriving first. Let us consider a charge Q. So why not minus Q? Why is that Q? So because it is only an assumption. Why not minus Q and why Q? I will explain it a bit later. Just understand this thing. Let us consider a charge Q placed at a point O. This is your point O, and P be a point at a distance r from O, at which we shall be calculating. Okay, this is our point under consideration. So P is a point. What is the distance between O and P? It is R. Further continuing it, we see that let us imagine a spherical Gaussian surface, and a Gaussian surface can be anything, can be any anonymous thing, can be any random shape, but it should be closed. It should be closed. Let us imagine a spherical Gaussian surface spherical Gaussian surface. Okay, it is done. Whose center is at O and P lies on its surface. Okay, so we need to make it a bit smaller so that this is your P, a bit more smaller, small. Okay, this is your point P at which you want to calculate your electric field. This is your spherical Gaussian surface, and by Gauss theorem, or the surface integral of electric field due to this charge at point P is the surface integral of electric field at point P is, so closed integration E dot ds. Okay, since P is equidistant from, or P is at a radius r from, or distance r from charge Q, this point is also at a distance r, this point is also at a distance r. That means any point on this surface, at that point we have the same electric field. That means at this surface radius r, electric field is constant. You can actually, and you can see that electric field is going this way, radially outward. This is E, and area vector is also radially outward. This is S. That means angle between E and, or you can include also here, E is radially outward edge well edge ds. So the angle between E and ds is 0 degree. If angle is 0 degree, then you can write E ds cos 0. Since dot product is cos theta and theta is 0 degree, so closed surface E ds. As E is constant, get it out of your integral. Since it is a closed integral, the total surface area, if we integrate this equation, we will get the total surface area. So total surface area of the sphere is E into 4 pi r squared. So as the surface area of sphere is 4 pi r square. Now apply Gauss theorem. Apply Gauss theorem. The same, it will yield us the same thing, that E dot ds is equal to q by epsilon naught. Since q is the total charge enclosed by our Gaussian surface, so this thing or this thing is equal to this thing. So since LHS is equal to LHS, both sides, left side of the equation are same, that means the right side of the equation are also same. You can name it as equation 1 and here it is equation 2. So let me check the height. Okay, it is quite visible. So equation 1 is equal to equation 2. Due to these consequences, we can write E into 4 pi r square, E into 4 pi r square is equal to q by epsilon naught. And these consequences lead us to E is equal to, just taking 4 pi r to that side, to the right side, it will get divided, is equal to, and rearranging them again, will get 1 by 4 pi epsilon naught q by r squared. Q by r squared. So you get the electric field at point P, which is at a distance r from that charge Q. You get electric field. And now you know that force, let me go a little bit lower. Now if we place a charge q naught at point P, q naught at point P. Now we have placed a charge at point q naught or point P whose magnitude is q naught. Then force on that charge, as electric field is E at that point, then force on q naught is F equal to E q naught. We have known this earlier, that force is equal to E q naught. Now just replace everything. 1 upon 4 pi epsilon naught q by r squared into q naught. See, just rearranging again, you can find that 1 by 4 pi epsilon naught q naught by r squared. This is your Coulomb's law. This is your Coulomb's law. You can actually observe this thing from here. This is Coulomb's law. This is Coulomb's. So you can actually derive Gauss law from Coulomb's law. I think it is visible to you. Sorry. After rearranging things, you see that you place the value of E calculated earlier at this point, which will give us 1 by 4 pi epsilon naught q by r square into q naught. And after rearranging things, F is equal to 1 by 4 pi epsilon naught q naught by r squared. and this is Coulomb's law in electrostatics. Coulomb's law of electrostatics. So it is enough to confuse you that whether it is the basic law of electrostatic or Gauss law is the basic law of electrostatics. So I will give you a clarification in the next lecture, and up until then you just have to think about it. So the ink in my pen is over, so I have to refill it. You can wait for a minute. Before jumping into another topic, I think I have missed something earlier. Some information about flux. Okay, some information about flux. So flux can be, what can be the value of flux? Flux can be positive, flux can be negative, and flux can be zero. Flux can be positive, negative, or zero depending upon the situation. What situation you have to check here? What is that situation? So if we consider an arbitrary shape object, an electric field is going through this way. An electric field is like this. You can make these lines a bit closer. Okay, a uniform electric field is like this. This is electric field E. And see, at this point, the normal to the surface is this. Okay, ds. At this point, normal to the surface is like this, and at this point, normal to the surface is like this. Why am I drawing such things? Okay, it's because you have to identify the angle between these 3 points. Okay, so if I am to calculate electric flux at such points, then I shall be writing phi E is equal to E dot ds, which gives me the value E ds cos theta. So flux depends upon E, it depends upon ds, and it depends upon cos theta. So the value of cos theta is, cos theta का वैल्यू -1 से +1 तक वेरी करता है. cos theta का वैल्यू -1 से +1 तक वेरी करता है. So it depends upon theta. If theta 0 less than theta less than 90 degree, then it is positive. It will give you positive. If theta is like this, then it will give you negative. And now we get these things at 90 degree. When it is at 90 degree, it is 0. Why it is 0? When theta is between 0 to 90 degree, then cos theta is positive. Okay, let me write then. Cos theta is positive. If E is positive, ds is positive, and this is positive, then the whole thing is positive, which means it will give you a positive flux. Now, if E is positive, ds is positive, and for theta inside the limit 90 degree to 180 degree, cos theta is negative. Cos theta is negative. Okay, if cos theta is negative at this, in this term, then the total term is negative. So if the total term is negative, you can say it is negative flux. And now if it is 90 degree, then cos 90 is equal to 0. Cos 90 is equal to 0. Then flux is 0. Okay, then flux is 0. So this, whatever you have understand, you apply to at this point. See, at this point you see that theta 1, it is theta 2, and it is theta 3. Okay, so theta 1 is, you can see that it is an acute angle. Theta 1 is an acute angle. Theta 2 is greater than 90 degree and less than 180 degree. And at this point you can see that theta 3 is exactly 90 degree. Is exactly 90 degree. And in this case, as we have considered these things, this is flux, positive flux. Whatever you will get positive flux. At this case, it is negative flux. It is negative flux. And in this case, it is zero flux. So there are three types of flux: positive flux, negative flux, and zero flux. And what is its significance? We will understand that in the later chapters, okay, or in the later classes. Why positive, why negative, and why zero? Okay, let me give you a just a crude concept. Your object is like this. Okay, your object is like this, and it encloses a positive charge. Then flux is coming out of the object. Flux is coming out of the object or the Gaussian surface. This type of flux is positive flux. And in any case, it is an object, minus q is here, then flux is getting into the object. It is negative flux, positive flux. It is positive flux. In this case, it is positive flux. In this case, it is negative flux. Okay. And I would like to, and you have also seen what is zero flux in the previous diagram. You have seen that flux is entering to the object and getting out of the object. So the number of flux lines entering the object is equal to the amount of flux getting out of the object. Then the net flux through this object is zero. It is zero flux. And also आप ये भी समझ सकते हैं कि ये ऑब्जेक्ट कोई चार्ज एनक्लोज नहीं कर रहा है. दिस ऑब्जेक्ट इज एनक्लोजिंग ए नेट चार्ज जीरो, a zero net charge, and hence the zero flux is, and through this object flux is zero. If it contains positive charge, it encloses a net positive charge, then positive flux is coming out of that object. If that object, that closed object, is having negative charge, then negative flux is going through that object, and if it contains a zero net charge, then zero flux is going through that object. So you get a rough idea of that. Now we shall be studying some applications of Gauss law. It is quite simple. So what are the applications of Gauss law? Applications, one application is we can actually calculate the electric field. Electric field of a line of charge, You are given a line of charge and you have to calculate the electric field at a distance r. So what is a line of charge? This is a line of charge and it is positively charged. Okay, it is uniformly positively charged and it is infinite. This continue this side, this continue this side. It is infinitely long and we are considering just a section of that wire. So let us consider a line of charge, or you can say, or a uniformly charged, infinitely long wire. Your wire is infinitely long but charged uniformly. Let the charged density. As you know, charge density for linear charge is lambda. Unit of lambda, what should be the unit of lambda? Coulomb per meter. Let the charge density is lambda. We need to calculate electric field at a point P from the wire. So you have been given a point P. This is P, and you need to calculate electric field at point P or electric field due to this uniform distribution of charges. Okay. So it should be uniform. So let me just make it a good diagram. You can use a scale to draw good diagrams. So you are just considering a section, only a section of that uniformly long charged wire. It should be positively charged. It is plus, plus, plus. You can make a thicker line. So it is positively charged and the density is lambda. So we need to calculate field at a point P. The distance between that point is R. That point is P. Okay. To calculate this, we have to use Gauss theorem. And how is that? Let us, and to evaluate electric field via Gauss theorem, we need to consider a Gaussian surface. In this case, it is going to be a cylinder. Let us consider a cylinder whose axis coincides with the wire. Its length is L and radius is R. So आपको पता है कि सिलेंडर ऐसे दिखता है एंड उसका एक्सिस क्या है? यह है उसका एक्सिस. And in this case, this is my cylinder, and since this is R, we can draw the cylinder right from here. Let's forget P for now. This is long, okay. This line is much longer. This line is much longer. The length is L. This length is L and radius is R. And this axis of the cylinder should coincide with the wire. Okay. So, what should be the electric field? As you know, since it is a positive line of charge, electric field is directed in this direction. Flux can go out through this surface, through this surface. It can go out through any of the surface. Okay. So now you have to consider these surfaces. This surface is DS1 elementary surface. This is ds1, and since it is the top of the surface, so the area vector is has a direction upwards, and in this case you are going to consider ds2. This is ds2. It is also the area vector is pointing downwards, and in this case this is ds3. So to calculate electric field just by Gauss's theorem, E dot ds. Okay, we are going to calculate the flux E dot ds through every surface. So first of all, it should be E dot ds1 plus E dot ds2 plus E dot ds3. Since you can see that this is our required equation, so you can actually see the three things electric. From this point, this thing is not clearly visible, so you need to make it here ds3. Okay, now you can actually see this is S1, S2, S3. So let us name this surface as S1, this is S2, and this is S3. For E ds1 cos theta 1, this is S1, plus E ds2 cos theta 2, this is S2, plus E ds3 cos theta 3 for S3. Now consider S1. You can see that what is theta 1. As electric field is always going to this side, you can see that theta 1 is equal to 90 degree. Theta 1, this is our observation, theta 1 is always 90 degree. And in this case, what is cos theta 2? Since it is also going this side, so theta 2 is also 90 degree. Theta 2 is also 90 degree. And for this integral, what is theta 3? See, electric field is radially this side to the going to the right and horizontal, and ds3, the direction of ds3 is also horizontally right. So angle between this is ds3 also. Angle between ds3 and E is 0. Theta 3 is 0. So just put these things. E ds1 cos 90 plus E ds2 cos 90 plus E ds3 cos 0. S1, S2, S3. See, cos 90, the value of cos 90 is 0. It is 0. It is 0. And cos 0 degree is 1. So we get a contribution from this surface, from the curved surface, and for the flat surface they do not contribute anything, as they are aligned at an angle 90 degree from electric field. The angle is 90 degree, this angle is also 90 degree. So they do not contribute. The flat surfaces do not contribute, but only the curved surface contributes. So I will write the curved surface contribute electric flux. Okay, you just know the region. Why? Because they are aligned at an angle 90 degrees. So let me get a bit lower. We need to finish this. So what is E dot ds, which gives E dot ds is actually S1 E d S1. Since at every of these points, these are equidistant points from this line of charge, so electric field is constant. If electric field is constant, you can actually take it out from the equation. Eg ds1. If we are going to, this is our elemental area on the curved surface, and if we integrate this elemental area on the curved surface, it will give the total, that curved surface area. So what is the curved surface area of a cylinder? As you know, what is the curved surface area of a cylinder? Then this point, then this thing E dot ds is equal to E into 2 pi r l. Okay, the curved surface area of the cylinder is 2 pi r l, where l is the height of that Gaussian surface or length of that Gaussian surface under consideration. From Gauss law, from exactly same Gauss law, you know that E dot ds is equal to q by epsilon naught. Q by epsilon naught. Do you know q? You do not know q. So you write E into 2 pi r l is equal to q upon epsilon naught, and E is equal to 1 by 2 pi q by l epsilon naught into 1 by r. All these things are going to this side. As you know, q by l is your charge density, is your linear charge density, that is lambda. So you can replace q by l is equal to lambda. 1 by 2 pi epsilon naught lambda by r. This thing is your lambda, and lambda by r. So electric field is quite interesting in the case of a cylindrical distribution of, or a linear distribution of charge. You can see that electric field is equal to lambda by 1 by 2 pi epsilon naught lambda by r. So at this point, write a bit more, 1 by 2 pi epsilon naught lambda by r. Okay, this is your required electric field answer. This is your answer. And for a linear thing, and if you want to make it simple more, multiply 2 on the numerator and 2 on the denominator, which will give you 2 lambda by 4 pi epsilon naught r. Okay, and then you can actually put the value of 4 pi epsilon naught r, 1 by 4 pi epsilon naught r, that is 9 into 10 to the power 9. And actually, so lambda is given, r is given, and you can actually calculate electric field for a linear charge distribution. And this was what about calculating electric field of a linear charge. So I understand that you have understood the concept very well. Sorry. You can take a good view of the thing. Okay, I think you got good view of that thing. So if any problem arises, you can actually take help of that comment section, and I shall be giving you response whenever any doubt arises. So from this point, I am stopping the lecture, and we will meet at the next lecture. And up until then, see you, take care, and practice, keep practicing. Okay, thank you.